Thanks for taking the time to watch this video. Just a note before we get started with the solution that if you're ever interested in one-on-one tutoring, I do meet with students via Google Meet as well as Zoom for private one-on-one tutoring. If you're interested in that service, feel free to contact me at this email address and I can provide you with additional information. On to the solution. You might want to take a moment to pause the video and reread the problem, but in part A, we are asked to find a demand function, assuming that that function is linear. So of course we need to understand what a demand function is. We have defined that in part A here. It says a demand function is the price P as a function of ticket sales X. Now again, in this case, it is linear. So what we're going to do is we're going to extract 2 points on this linear demand function and then use those 2 points to come up with the equation of that line. So for example, we are told that when the ticket price is $10, then the attendance or the number of tickets sold was 27,000. So we can translate that into a point. We have 27,000 tickets sold and then at a price of $10. So we would set that as our X and Y for our first point. We then read on, and there's another point. When the ticket price was lowered to $8, then ticket sales rose to 33,000. So that would be a second point on this line. We have 33,000 tickets when the price was $8. Notice that the number of tickets is the X, and the and the price of the ticket is the Y. So now what we're going to do is use those 2 points to come up with the equation of a linear function. Now you probably learned in pre-calculus that a linear function in what's called point-slope form can be written in this manner. And in order for us to progress here, we're going to actually want to find the slope first. So of course the slope is m. So we're going to do a little aside as a calculation here to find the slope. And we probably know that slope is the change in the y-coordinate divided by the change in the x-coordinate. So what we'll do is go back to our points. We will label the first point as x1, y1, and the second point would be our x2, y2. And then what we'll do is take all 4 of those numbers and plug them into our slope equation. And then we can simplify this by just subtracting on the numerator and the denominator. We end up with this outcome. And then when you reduce that fraction, you will see that the slope is negative 1 over 3,000. So we're going to take that value and plug it in for m into our linear function. The next thing we're going to do is select that original point. If we go back up and look at that point, we see that the x1 was 27,000 and the y1 was 10. So we're going to plug those values in for the x1 and the y1 in this linear function. And then we'll distribute the slope value. So we're going to multiply that slope by x and by the negative 27,000. When we do so, we're going to get negative 1 over 3,000 times x, and then plus 9. Notice it's a plus 9 because we're distributing a negative to a negative 27,000. We then just add the 10 to the other side, and we are left with that outcome. That is the answer to part A. This is a linear demand function. Your professor might want you to write the y as p of x instead, but that would be an equivalent form of this answer. So part A is complete. We have our demand function. Let's go back up and look at what part B is asking us for. In part B it says how should ticket prices be set to maximize revenue? So revenue is the next concept at play here. So let's take a look at the definition of revenue. So revenue is going to be the quantity, which in this case is the number of tickets sold, multiplied by the price per quantity, in this case the price per ticket. So in symbolic form, we're going to take x, which is the number of tickets sold, and then multiply that by the demand function. Now, of course, we already came up with the demand function. So in this case, we're going to have r of x is equal to the quantity x multiplied by p of x, which again is above on your screen there. So we're going to fill that in for p of x. That's our revenue function. We should probably simplify it before we progress. So let's go ahead and distribute the x. That'll make our lives a little bit easier. So now we have r of x is equal to negative 1 over 3,000. This becomes x squared, and then plus 19x. So that would be the simplified revenue function. And again, in the question, we are looking for the ticket price that would maximize revenue. So any business typically would want to maximize the revenue coming in. That's what we're going to do with this function. And you might notice that this is a quadratic function. We know it's a quadratic because it's x squared. We also have a negative coefficient of our x squared term. So this would actually be a parabola shaped like this. And we can see, and this is kind of a crude sketch, of course, but we can see that an upside down parabola is going to have a maximum value. And that maximum value occurs at a particular x, but it also occurs, let me just slide this over, at a particular y value. So that's kind of the point that we're interested in. And if you look at that point, you'll notice that if you drew a tangent line at that point, then the slope of that tangent line would be 0. So in calculus terms, we would say that the derivative, the r prime of x, would be equal to 0 at that maximum point. So of course what this means is we're going to have to find the derivative of our revenue function. And then we're going to set it equal to 0. So here we go. We're going to find the derivative. We're going to find r prime of x. So we're taking the derivative of our r of x function. And to do that, we'll just use a simple power rule. So we're going to multiply the power of 2 by that coefficient. So we'll get negative 2 over 3,000. And then our variable x will be now raised to the power of 1. Remember, you have to subtract 1 from the original power. So now we have x to the 1. And then over here, the derivative of 19x is just 19. You could even use a power rule there, of course. This is a power of 1. 1 times 19 is 19. And then you get 19x to the power of 0. But x to the power of 0 is 1, so 19 times 1 would give you 19. So that's kind of the longer way of finding that derivative. But there is our revenue function. And as shown in the graph, we're going to take our revenue function and we're going to set it equal to 0. So let's kind of scoot down here so we have some room. We will set this equal to 0. Let's subtract 19 from both sides of the equation. And then to continue solving for x, we're going to multiply both sides of the equation by the reciprocal of that fraction. So multiply by negative 3,000 over 2. You're going to do that on both sides, just like that. And then when you do that, the 2's cancel, the negative 3,000's cancel. You're going to be left with x. And then you can punch this into a calculator, and you're going to see that x is 28,500. So that is the x value at which the revenue would be maximized. Now, some professors, if this were a test question or a homework problem, would want you to prove that this actually maximizes the revenue. We did draw a rough sketch to show that it maximizes revenue, but again, your professor might want you to prove it. And one way of proving it is to use something called the second derivative test. So what we would do is take our first derivative, which was the r prime of x was equal to something. It was that negative 2 over 3,000 x plus 19. And then compute the second derivative. So we're going to do r double prime of x. Now the derivative of the first term here is just going to be negative 2 over 3,000. And then the derivative of the 19, which is a constant, is just 0. So the second derivative is negative for all values of x. And you might wonder, well, what does that tell me? Well, because the second derivative is negative, that tells us that our revenue function is always concave down. So if you think about that point that we found earlier, where the x was equal to 28,500, well, the second derivative tells us that the function is concave down, and that shows us that indeed it is a maximum. So your teacher would probably want you to say that this is less than 0, which is just a fancy way of saying it's negative, and therefore, according to the second derivative test, the revenue is maximized. And that is maximized when x is equal to 28,500. Now the question did not want the maximum revenue. It did not want, let's see, what did it want? Why don't we just read it? It says, how should ticket prices be set? Okay. Well, we found x, but x is the number of tickets sold. It doesn't tell us the price. It's not as though the price of the ticket was $28,500. That would be quite a steep price. So we have to find the price, but we can do that. We just go back to our demand function. Remember, the demand function is the price as a function of ticket sales. So we're going to copy and paste our little demand function. We'll bring it down here. And then what we're going to do is we're going to plug the 28,500 in for x. And then when we simplify that, you can punch that into a calculator. You will see that the ticket price turns out to be 9.5 or $9.50. This is the final answer to the question. That is the ticket price that would maximize the revenue.